So on 925, we talked about plasticity, and specifically this is where I gave you the Drucker-Prager model. Right? So it's there. Okay. I also here, if you go back and watch the video, what I was doing in this sort of line right here was I was explaining that now our flow rule, which includes this term, right, partial f. So this is the yield function. So partial yield function with respect to sigma j, and you know this arrow doesn't mean it's equal. It just means that I was just meaning to show that we already know what this term comes out to. It comes out to s, right, Sij. But then we have this term, and if you take its partial derivative with respect to sigma ij, then you get this guy, right? 1/3 delta ij beta. So this needs to be included in your flow rule, and I'll write that down in a second. But and then you had the question about, well, what about this thing? Like what, do we need to take the derivative of this with respect to sigma ij? Because I see why you think that, because you sort of say, well, ultimately we solve for these plastic strains through this return algorithm, which is a function of the yield surface, which is a function of the stress, right? Yeah. But for our practical purposes, it's at any instant in time, it's a constant with respect to the stress, because those plastic strains are internal state variables or history variables. And so, we had in general, you could have the yield function as a function of these guys. I think I had even written temperature, right? But here's the thing. So let's consider the case. Let's consider the case of isotropic hardening, right? And let's define, so here's the sort of yield stress, or, the elastic limit. And let's define sigma 0 to be the increase, so it's this distance, right? It's the increase above the elastic limit, right? And if this of course, is h, right? So then I can write an equation, or I can say that, d theta dep is equal to h, right? The slope is h, right? That guy. Okay. Which means I can rewrite that like this, and then I can integrate both sides such that I get this equation, which basically says that the stress, or the increase in stress above the elastic limit, is at any instant in time is completely determined by the history, by essentially the material properties and the history of the plastic strain. And so at any instant in time, it's a function of the history of stress, not the current stress. Right? That's why you don't have to take the derivative of that term. That's for sort of our purposes, it's a constant, right? So for the Drucker-Prager model, we had that, our yield function, which now is a function of pressure and J2, is equal to the square root of 3 J2 plus beta P minus Y. And in this case, Y is only a before I'd written a function of plastic strain rate, and temperature. But in our case, it's just isotropic hardening. So it's
minus before beta or plus?
I think it's plus. And, huh? Okay. I think it just depends on the convention for the sign of pressure, but so it doesn't matter.
So in this case, P is minus 1 over.
Yeah, okay. Yeah. But it really doesn't matter, right? You understand? It's just a sign convention for what's positive pressure, right? And it's really confusing because in mechanics, everybody uses compression as negative, right? But in geomechanics, everybody uses pressure as positive, compression as positive, right? Because in the Earth, You really only have, for the most part, compression. So, and because of that, because I live in both communities, I go back and forth and and confuse my students, I guess. But ultimately, it doesn't matter. You just have to flip the sign in the pressure term. Okay, so yeah, so and we have a flow rule. I said use an associated flow rule, right? Which for soils may not be a good idea, but for simplicity, that's what I told you to use, right? So here's our associated flow rule, and we also wrote this as Qij, right? So this is this is like the direction of a normal vector to the node surface. And we could also write this without this denominator, and then just in the solution process, then the vector would be the same direction, it would just have a magnitude. So when you solve for your multiplier, it would be a different value. But it's something you're eliminating anyway, right? It's just it's a constraint multiplier that you're eliminating in the solution process. So it doesn't really matter if you carry this or not. But if you later want to use the sort of framework I set up for incremental plasticity, then you might want to have that Qij. So you might want to do it this way. Okay. So then, now this guy is Sij minus 1/3 delta ij beta.
I think that's it has a square root of 3/2. Because it was like 3j2 and then so the f was like the square root of 3j2 and then
yeah.
Square root of 3/2.
No. I think it works out because J2 is 1/2 Sij Sij. We did it I think I even did it in the notes. This is the 25th.
I think it was probably
23rd.
I mean, in that place because it was like he said f is
It's on the classical.
Hmm?
It's classical on the beginning of 25, 27.
Right here.
Yeah, that. So, but then that's we just that's the square.
Oh, this is okay. You're saying this is only
the J2.
the J2. Okay. Yeah. So you're right. You may have square root of 3. Yeah. Again, this is one of those things that doesn't matter, and you'll see it differently. Sometimes you just see the square root of J2 there. You don't always see the square root of 3. All that does is
your yield surface would be bigger or smaller.
yeah, but ultimately the stresses you compute will be the same.
It should affect. I mean, if you're on bigger yield surface and then.
Well, once you get into the plastic regime, because I know, you know, if I'm thinking about it when you see it with respect to Tresca criterion, which is like a hexahedron thing, it just means that it's either inside or outside that thing.
Because ultimately you want to return, right? And your new surface.
But this is right. This is right. Right? This is right. This is equal to 0. See, this is right. This is equal to 0, right? So I can move the y to the other side and square both sides.
Yes.
And divide by 3. And then I compute the derivative of that. The derivative of this with respect to sigma j is 0, and I just have the derivative of
Yes.
that. So that's correct.
Yeah, that is correct. But then in the Drucker operator, that's correct. In the new Drucker operator, when you can't like.
Oh, I can't because I can't move it over.
Yes.
You're right. You're right. Yeah. So you'd have the square root of 3j2. You're right. Okay. Yeah. So that. Right. Sorry. I got it.
Does
Or-
it have it out? Because like yeah, maybe because of the square root.
Maybe
I mean I initially wrote like the square root of 3 over 2, but I know it does have the square root of 3.
Yeah. So let's see. Yeah, I mean, okay, square root of 3. Because you can always, you can move it, I mean, it's just a constant. You can move it outside when you take the derivative, right? So, yeah. Okay.
Should I say in the square root? Because you know previously we said d sigma I j of j2 was like
Yeah.
inside j. But now we have the square root here.
Yeah. I mean, we could work it out. But so another way, let's do it this way. Let's look at I guess I should have worked it. Probably should have worked it out all the way here. All right. Well, let's do it this way. We have square root of 3j2 is equal to beta times the pressure minus k plus minus plus. Right. So then j2 is equal to 1 over square root of 3 minus b plus k. You okay with that?
Yeah.
Okay. Now take the derivative of both sides. We know absolutely now the derivative of the left-hand side is Sij, right? Okay. We've established that. So then the derivative of this side, we just use the chain rule, right? times and that term we've already established is delta ij, right? Is 1/3. We've already established that.
Yeah.
And again, there's 1/3. Okay. Now we could, you could simplify it if you want, but that's what it is. Okay. All right. So then then this guy is equal to the square root of Sij, right? Where Sij is that thing. And again, it's messy. Like if we want to work it out by hand, it would sort of be messy. But if you have a computer, you're already computing Sij. Just compute Sij, and take the square root of it. Right? So then we have Q, right? So then Q is and then it's back on the 23rd. So then we work through all of this, which all of this just comes from the additive decomposition of the strain rates, right? So you ultimately start working through, and you get this equation, which again just comes from the additive decomposition of the strain rates. Okay, so that was again like on the 23rd. Okay.
There's one thing there. So that S dot ij times qij, what happens to that? So because now the qij, now is it equal to S dot exactly, or is that it has terms of like beta p or something in it? Or the S dot?
Well, S dot has the same terms in it. Because they point in the same direction, right? Q is a unit vector in the same direction as S.
Okay. And then now,
No matter what direction S is. Right?
so let's say now qij is like df d sigma divided by its magnitude. Is that it? And then now Sij is what? Is that f by essentially? I think. Yeah. I think it's
We are taking a derivative of f with respect to sigma ij only for calculation of qij.
Yeah, essentially, yeah.
Then we follow just this procedure
Mhm.
to come up with the equation for the.
Yeah. So we have this guy, and then jumping ahead. So this was all sort of theory or continuum, right? We at this point we're just talking theory. We didn't have a computer yet, right? And then jump ahead to think the 1113. Now we're talking about computational plasticity, right? And here we start with the same continuum equation, but then we introduce discrete quantities. Okay. So that ultimately you have this equation, right? Which the only unknown in it is delta lambda. Once you substitute in your yield function, which in this case there's no strain rate term, so it's just, you know, the yield function is the quasi-static yield stress plus h times the plastic, an equivalent plastic strain, and all of this at the n+1 time step, right? We're doing fully implicit. So all of this at the n+1 time step. Like instead of using this one, you just use the hardened one that I told you. And the rest of it follows through. It just also keep in mind that when you need to evaluate the pressure, you also want to evaluate the pressure at the n+1 time step, which is, so then you have the old pressure plus the increment, plus the bulk modulus times the increment of total strain.
One more question about the if statement when we decide on whether we are in plastic region or not. So for if statement, we don't need to include epsilon p, strain p yet, because we only want to know whether we are in the plastic region or in elastic region. It doesn't matter if we are at the beginning of the plastic region or at the end of the plastic region.
It's a little more subtle than that. Okay, so you can have an initial if statement that checks for, like, if it's above the quasi-static yield stress, right, or above the previous value of the yield stress, right, or below. If it's below, it's unloading and it's elastic. If it's above, then you might be plastic. And the reason I say you might be plastic, right, so if it's above, okay, you might be plastic. The reason you might be plastic is because you're taking a step, and over that step, the yield surface grows. Because the yield surface is a function of the plastic strain.
So how can we update the epsilon p?
So you have to, well, it just...
Because in our case, we don't have any unloading yet.
Yeah. So you'll always be, you'll always be plastic.
If it's above the...
If it's above where it was, if it's above where it was,
Yeah.
you're plastic, because there's no unloading.
You have to.
No, I mean, we don't need to include the epsilon p.
In your yield function, you ought to.
Well, ultimately, when you update Sn+1, you do, right? Because so you're going to take a trial. You're going to take a trial elastic step, right? You're going to take a trial elastic step, and you're going to evaluate your yield function. Okay. And if it's then you're if this is true, then you're going to go on. If it's elastic, you're going to accept the trial stress as the stress, and you're going to move on. However, if it's plastic, then you have to update this guy, and this guy is a function of. I mean, you're essentially solving this equation for delta lambda, which is delta p. But then when you update your stress, you need it, right?
Yeah, for updating we need it, but for checking whether it's below the 0 or equal to 0, we don't need the
because you're essentially at that point you're solving this equation for delta lambda, right? So you need the old values, but not the n+1 values. You get the n+1 values from delta lambda.
Yeah, but you use the epsilon p like n in it, right? I mean, like
Yeah. Because epsilon p n+1 is n plus 2/3 delta lambda. Right?
Yeah.
So, and then y is a function of n+1. Right? So when you update the stress, you have to evaluate, at that point you've solved for this. You solve for this because you've solved f equals 0, f dot equals 0 essentially. So you have this in hand now. You update, you plug it into this equation. That's the old value, right, for the previous step. So you just plug that into there, evaluate your new stress, and then. So you don't. So you're right. I mean, you would take a trial stress and you'd evaluate. You'd ask yourself, am I above where I was, right? Because
I'm asking that where I was in the previous step, or whether I am in the plastic region or not. In this, what's the question there? I'm asking that am I above the previous step, or
well, when you take your trial elastic step, at that point, the only thing you know is where the thing was, right? So that you're comparing it to the previous value, yeah, in that case. The trial step occurs at the n+1 step, right? I take at every step, at every load step, at every increment of displacement, I evaluate the stress as if it's elastic, and then I ask the question: is it elastic or plastic? And the answer to that is by comparing to the yield surface, and the only thing I have is the yield surface at its old value, right? At that point. So I compare it to that. If it's inside the yield surface, it's elastic. You accept the trial step and go on. If it's above it, then you have to solve for delta lambda to determine where it is.
But if it's growing, doesn't it mean that if we are comparing this point to the previous stress, might be less, but it's actually still on that surface?
That would be the case if delta lambda was 0, right? Then it would remain where it was.
I mean, if we calculate...
Because yield surface, in this model, in most models, the yield surface doesn't shrink. It only grows.
So I think the question was like, if you draw the stress strain curve, and like you have this linear part, okay, and then now you're at this part at this point. In the next step, you're going to use in your f function to see if the new point is on the plastic region, on the plastic surface, on the yield surface or not. You're using the epsilon p at this step, at the previous step, or n+1. So yeah, we were discussing, like you were suggesting like epsilon p is 0 for the previous step, but I think that's not the case.
No, I don't think. I think your idea to draw a picture helps, right? So say at
This is n, for example.
this is epsilon p n, right? So at epsilon p n+1, you're going to evaluate a trial elastic stress, right? So you're going to evaluate the.
Let's say epsilon p n+1 would be bigger, right?
Yeah,
So
it is big. It is bigger, right?
The epsilon, the x-axis. There is the final point of the red one is your epsilon p n+1.
Oh well, yeah. I mean, I'm going to run out of room, but yeah. Yeah.
Yes, it's like.
It's over there, right? Yeah.
Like maybe we can just use this little.
Let's do it again. Better? All right. So, yeah, so then, this is your trial elastic. stress, you're obviously well above the yield surface, right? And so then the job is to compute the accumulation of plastic strain. How much did the yield surface go up?
Yeah. And I think if we use the previous epsilon Pn, so it's like we use the red slope will just continue, but then since we are yielding and we have like linear, like we have hardening, so it would be like a little bit bigger than that. Am I right? Like the triangle search is off for sure.
Yeah.
Our result will be the same as the isotropic, just isotropic hardening case. Yes, it will be straight line.
Would it have some curvature?
If you look, if beta were 0, yeah, it would reduce to isotropic hardening. I mean, that's one way to test it.
Even if the beta is not 0. Should there be any curve?
Under pure shear deformation, yeah. Under pure shear, you'd have something like that. Yeah.
Something curve.
Hmm?
Something.
Well, if it's pure shear, then the pressure component. I mean, if you have some compression, then it's going to affect the slope. Yeah. So the way to test it is to set beta equal to 0 and see if if the slope of that line is h. And then you can that verifies that the hardening is working properly.
So P is also linearly dependent on the strain.
The strain, not the plastic strain, though. I mean, the plastic strain. The pressure component is only a function of the strain, not the plastic strain.
Ultimately, we're calculating the pressure based on like the summation of the sequence, right? The pressure is like one, like the sigma 1 plus sigma 2. So whatever we have in sigma, which like is a function of everything else.
But it's yeah.
So I mean, we don't care about P specifically. So we care about the espresso.
Yeah.
P is just.
But the Pn plus 1, you're going to update by multiplying, taking the old pressure, right, and adding K times the total strain, times the total strain times sigma ij.
But that was for probabilistic thing. That was the pressure itself, right? That P that you showed was for actual pressure. But here it's like the P that we are using here is like minus 1/3 of sigma 1 plus sigma 2 plus. It's like
Yeah. This is the hydrostatic pressure.
This is the true pressure.
The hydrostatic pressure is defined by the trace of the stress tensor. Yeah, not the. Maybe I going forward I should use pH or something to make that distinction. Not the pore pressure. The hydrostatic pressure. Yeah. Any more questions?
I think if we calculate F with EP, even if previous time step, it wouldn't change the result because it's just the if statement. Yeah? We are checking whether, and we don't have any unloading, so it should give the same result.
I agree. Yeah, because it's monotonic loading.
So to make it easy, we can exclude EP in F calculation.
Oh yeah, I mean I see what your question is now. Yeah, you're just saying if it's above the elastic limit,
Yes.
it's all, and because we're monotonically loading it, we
Yes.
can always load. We're just always going to be plastic. Okay. Yeah, you can do that, and in fact, you can always do that. You can always do that. Just say if it's above the elastic limit, then I'm gonna, I'm gonna assume it's plastic and move forward, But in the case of unloading, you'll compute a negative delta lambda,
Yes.
and then you just discard that. You just say, okay, well, it's in fact is elastic. The delta lambda can't be elastic. It can't be negative. If you remember, that's one of the Tucker conditions, right? Delta lambda must be greater than or equal to 0. So yeah, so you can always do that. Then you just have to check, is delta lambda positive or not? Right. And then that's how you determine it, if it's in fact is yielding. The reason that you might want to sort of actually evaluate the yield function with the old value of plastic strain is it does save you a little bit of computational time in the event that you're unloading, and you can determine it immediately. So, but for this problem, once you go plastic, you're always going to be plastic because you're monotonically loading it.
Can you draw something?
Mm-hmm.
Can I draw?
Yeah.
Like, let's say this is epsilon P, and then like from here, the next stress, the trial stress would be like here.
Mm-hmm.
That's one, and this is like this trial.
Yep.
Okay. The thing that we have like F equal to something.
Mm-hmm.
Right? So the fact that if he is suggesting epsilon, we can't ignore epsilon P in this equation, right?
For calculation
Yes.
of total.
So yeah. So the thing is, let's say, so if you're ignoring epsilon P, it's like we are on this line. It's like we don't. So if it was here, if in the new stress, in the new epsilon and P, if the stress is here, it means F is equal to 0. But if we set epsilon P equal to 0, it means we're here.
Yeah.
So is that
No, all he's saying, I think what he's saying is, in the if statement to check for
Yeah, the F.
are we plastic or not. Okay.
Yeah.
He's basically saying anything that exceeds this value, I'm gonna treat it like it's plastic and move forward. And in this case, you're always monotonically loading, so in fact you are going to be up here. Had it not, if it's unloading, you'd compute a negative delta lambda, and it can't be, and then you discard that solution and accept it as an elastic. So he's just saying, if I'm above here, I'm going to treat it like it's plastic. And in this case, there's no time wasting because you're always monotonically increasing. Right? So he's not. He's just saying in the if statement.
Yes.
just
Right.
like okay.
In the actual solution, you use it, right?
Yes.
Because you have a delta lambda in it. You have to. So the actual solution of f equals 0,
I was talking about that.
he uses it.
Yeah.
Absolutely have to.
Yeah.
And if delta lambda is negative, then you're unloading and you just discard that solution and accept it.
Yeah.
So, because I mean that what he would do if we had, you're exceeding this, so you're just going to treat every step like it's a plastic one, and then you unload. Remember your delta lambda is sort of what returns you to there, right? So it would be the opposite way. It would be negative.
Yeah.
And then you say,
Gotcha. Thanks.
this occurs a lot in viscoplasticity and other things where you can have a vast amount of change in the yield surface over a step, and you can even if you check from the, even if your if statement includes the previous value, and you start to, you say, okay, I'm going to treat it like it's elastic, but because of rate, because of your rate hardening, the thing, you know, in that case it would be like, you know, the thing jumps up so high over one step that once you evaluate where you really are, you could be below it.
Yeah.
And then you say, oh, I'm not really plastic. This is not trivial. I mean, you know, most of the time, you know, you don't really get to see this kind of stuff until you have to do it as part of your job or your research. It's very rare that you get to do it in class. Right? So, but now when you do encounter it, because you'll undoubtedly encounter it in your job or your research, or if you're working in mechanics. Now when you encounter it, you'll say, oh, go look at my old code and just pull out the return algorithm. You know? Anyway, so yeah, unfortunately I got meetings all afternoon today, but then, you know, starting next week I'll have a lot more time, and, you know, I'd be happy to come by my office. I'd be happy to spend as much time with you as you want. All right.